Thanks for the great introduction. So it's my pleasure here to tell about this work with my advisor, Andy Lucas, on these two kinds of problems. So I'll start with the metrology one, and later on you'll see the connection to the sampling. Okay, so first some basics about quantum metrology. Suppose you have capital N number of quantum spin-1/2s or qubits, and you want to use them to measure a magnetic field omega with high precision. If you start with an entangled state, then the best you can achieve is the standard quantum limit, where the position delta omega scales as 1 over root n. Here, the other parameters t is the evolution time during this omega times total z Hamiltonian, and the curly m is the number to repeat your experiment. Here, I focus on the m much larger than 1 regime, and I think in the next talk, you'll hear about more general treatments. With entanglement, you can do better to achieve the Heisenberg limit, where delta omega scales as 1 over n instead. And the simplest way to do this is to start from the GHZ state, which is all 0 plus all 1. And since it acquires a phase that is proportional to n, as long as you can measure this phase, you get Heisenberg limits for omega. And moreover, this can be measured simply by just projecting all the qubits onto the x spaces. So this kind of ideal quantum metrology is good. It brings us advantage, and we want to know its robustness against imperfections. Unfortunately, if you have some general decoherence, then the best one can achieve reduces to SQL. But there may also be situations where decoherence can be safely ignored, but there is still some unwanted interaction during the sensing that one cannot perfectly cancel. So that's the situation where we focus on, and this problem has been considered in the literature, mostly in the case-by-case studies. So here, we want to treat this in a more general framework. Okay, so let me define the problem more precisely. Suppose the n-qubit Hamiltonian h omega is this omega times total z plus a known v. We assume it is geometrically local, in the sense that the qubits live on the vertices of a bounded degree graph, and v is sum of terms that are finite range on that graph. In this setting, one can define a local strength J of this v, basically to measure what strength interaction that each qubit feels. We assume this J does not depend on n, but we allow for strong interaction where it can be much larger than omega. And this can be beneficial, for example, if this interaction is useful for maybe generating the original entangled state. So we use this h omega to evolve the initial GHZ states, get the final state psi omega, and we ask, is there a measurement protocol that measures this final state that achieves Heisenberg limit? Here we focus on the n scaling and are satisfied as long as the protocol can achieve Heisenberg limits at JT, which is order 1 constant, because then you can possibly scale this protocol up. So that's our first question. If this protocol exists, we also ask whether it is efficient to implement, because we probably don't want to measure some generic many-body operator. Instead, maybe we want some local measurement plus some polynomial time classical computation. Okay, so when thinking about this problem, we first have two observations. First, this problem is non-trivial in the sense that the original JC protocol that measures in the x spaces will fail in general. And it actually fails even if V is actually some on-site field X. And in this case, you can just calculate things exactly and show that the coherent part in this probability distribution is in general exponentially small. And furthermore, this argument suggests that for more general interactions, actually any fixed local basis measurement cannot achieve Heisenberg limit. The second observation is that our first question of whether a protocol exists is equivalent to asking whether the quantum Fisher information f of psi omega scales as of order n square. And as a reminder, this QFI is defined as intuitively as how fast this psi rotates in the physical Hilbert space. And this equivalence comes from this quantum Cramér bound, which is separable. Okay, so after these preparations, we're ready to state our main result. So we prove that indeed the QFI remains of order n squared before some order 1 time. And furthermore, this can be achieved by an efficient LLCC measurement protocol, which works as follows. You get this final state psi omega, you measure the spins 1 by 1, and the next local measurement basis is determined by the previous measurement outcome plus some polynomial time classical computation. So this protocol can be sketched in this way, where for the quantum part, one first measures the first spin using some given basis, and then one gets the outcome x1, which is either 0 or 1. Suppose it is 0, then you feed this 0 into a classical computer, and after some time, it tells you the basis E0, 0, E0, 1 to measure the second qubit, and so on. So what this does is to project its final state psi omega onto this adaptive local basis x. And the key point here is that one does not want to store all the exponentially many local bases in the classical computer, but just want to compute the basis that is chosen by your quantum experiment. Okay, so let me sketch the proof. First, why does QFI remains of order n square? Observe that if V is 0, then QFI is this ZZ connected correlation function in the initial state, GHZ state, summing over all pairs of qubits. The idea is that for general V, it is still of this form, which is ZZ kinetic correlation function, but now in some kind of time-evolved state psi. Let's say it's just the final state, and the question just becomes to show that the correlation cannot decay in some order 1 time. And this is actually very similar to how one proves that, say, long-range correlation cannot be generated in short time. And the idea is basically to move the time evolution from the state to the local operators. And since we know the dynamics is local, the local operators cannot evolve very fast. And that ultimately proves this QFI remains order n squared before some order 1 time. 2 remarks. First, if you actually restrict to a weak interaction, then we're going to show that Heisenberg limit actually holds for any time, and using some simple arguments from energy conservation. And second, this slide holds for any metrological resource states beyond GHZ state. So then I want to show the LCC measurement protocol. So there's already a known theorem which says that for the pure state metrology considered here, there always exists an LCC basis that saturates the quantum Cramér bound, so in our case, achieves Heisenberg limits. So I'd like to first show why this theorem holds, and further that for GHZ metrology, this LCC basis does not only exist, but also can be determined in polynomial time. So the idea is that for metrology, you are basically doing the following thing. You are measuring a logical in the 2D subspace spanned by psi and d omega psi. And I claim this task is equivalent to another task which may be easier to think about. It is to distinguish 2 orthogonal states, psi1 and psi2, still in this 2D subspace. Why? Because if you can distinguish, that is, if you have a measurement that such that psi1 and psi2 has non-overlapping support on this measurement outcome, then also for any superposition any superposition, you can tell what's the weight on psi1 or psi2. So for distinguishing these 2 states, the goal is basically to find the basis x such that this equation holds. And for simplicity, it may be more clear to massage it to this form, which basically says that these 2 traceless Hermitian matrices M1 and M2 have to be 0 diagonalized in this X basis. Okay, so how does one find an LCC basis that achieves this? One take the 2 M matrices, trace all qubits except 1, and we can find a local basis that simultaneously 0 diagonalizes these 2 2x2 traceless Hermitian matrices. And you can verify that this can be done by some simple single qubit rotation. And then when just project the global M matrices onto the first qubit, and then again trace out all the qubits except qubit 2. You get 2 2x2 traceless Hermitian matrices, and again you can find the local basis for qubit 2. And in the end, you can convince yourself that you achieved the original goal. Okay, so in general, this procedure involves this kind of many-body partial traces, so it is probably hard. But for GHZ metrology, we want to relate to the sampling problem in order to show efficiency. I claim that for GHZ, we can use psi1, psi2 to be the time-evolved all 0 and time-evolved all 1 state. If this red part is actually cat 0, brat 0, then these kind of many-body power traces are actually asking for the following question. So you start from the all-0 state, time evolved by some local Hamiltonian, and you first measure the first small n qubits in this measure outcome, after which you ask what's the local density matrix on the next one. If you can do this, then you can sample the measurement outcome because you can output the bits one by one. And here, although for metrology, we do not have a strictly speaking quantum state, but the mathematical structure is the same. So from now on, I will change gears to the sampling problem and just claim that we used the results there to prove the previous metrology theorem. Okay, so let me be a bit more precise. What do we mean by sampling? So suppose this Hamiltonian H is still geometry local on a bounded degree graph of local strength J. We also allow for some simple time dependence that it can contain a finite number of Fourier modes. And one evolves the all-0 state using this Hamiltonian, and LCC measures the final state psi. Sorry, there should be no omega here. And outputs string X. That's what the quantum experiment do. And we want to ask whether a classical computer can also sample this string X with a small total variation distance. So there are reasons to believe that this task is hard in the worst case if JT is larger than some order 1 constant, even in 2 spatial dimensions. And 1D is special where one can actually use matrix product state ideas to show the easiness before some log n time. And our main result is that for general bounded degree graph, actually, if you assume some extra condition, which says that the local measurement basis does not coincide with the computational basis, more precisely, the local 0 state, its overlap with the measurement basis is always larger than some order 1 positive constant. For example, this is satisfied by the X basis measurement. Then you can prove that before some order 1 time, there's a efficient classical sampler. Okay, so as for implications, as I said, this proves the previous metrology theorem where we can show this measurement assumption holds naturally. And also this proof can be easily generalized to show that before this order 1 time, long-range correlation cannot be generated by these local measurements. And so this also constrains the power of measurement-based quantum computation. Okay, so how does this sampling algorithm look? As I have touched upon, this is based on a standard reduction, which says that for sampling, it is sufficient to know this kind of conditional probability or marginals, which means that you have measured the previous small n qubits, and you ask what's the probability to measure the next one. And for this computation problem, we invoke this key lemma, which we call cluster expansion for real-time evolution. And in a nutshell, it says that this marginal can be computed in a sufficiently local region, roughly of size log n. And more precisely, you can it says that this marginal can be expanded in a convergent series of t if t is smaller than some order 1 constant, t star. And furthermore, the coefficient gamma m can be computed in polynomial time if you truncate this up to log n order. And that order is already sufficiently large so that this truncation error is as small as you desire, such that the sampling algorithm works. So in the rest of my talk, I would like to dive into a bit more detail about this cluster expansion lemma. Okay, so I think the name cluster expansion dates back to Meyer's work on weakly interacting classical gas, where he shows this calculates this convergent series expansion for the equation of states. And this kind of convergent series expansion technique is generalized to quantum lattice systems that we consider here, for example, by these 2 beautiful papers. And I think the most physical viewpoint is to consider the quantum Gibbs states, which is also the topic of this morning, where this lemma would be that the log of the partition function, you can always expand it in a convergent series of the inverse temperature beta, as long as beta is smaller than some order 1 constant beta star. So the physics is just to say that any geometrically local Hamiltonian is in the trivial phase at sufficiently high temperature so that everything is analytic. Okay, so in a nutshell, how does one prove this? The idea is relatively straightforward. One just Taylor expands in beta. So first, expand this exponential. One can get that the partition function z is a sum of these small h's defined by the HA, that's where each HA is one local term in your Hamiltonian H. And then you get z as this sum of small h, and one can further expand this log to a multivariate series of the small h. And then one can organize this sum into a sum over clusters, where a cluster is basically to specify what local couplings are included in this cluster and how many times they are included. And the key observation for the convergence is that one can further restrict to just connected clusters. For example, the cluster on the right, it is disconnected because you can it has non-overlapping support on the qubits. And after that, the most technical part is to count the number of connected clusters. And for each cluster W, one bounds this gamma W using the simple bound on the small h. If you can do this, then you are done with this lemma. And we basically want to generalize this kind of imaginary time evolution to real-time setting, which is also the topic of this paper. Here we want to show it for the sampling problem. Okay, so let me just highlight some of the key ideas. So first, we want to massage the form of the marginal into the previous skip state. So in order to do that, we want to rewrite this Heisenberg evolution, the green part, to a single exponential e to the TL, which is a kind of super operator that acts on the operators, which can be viewed as vectors in the operator space, such that then you can follow the previous slide, and where you can also restrict to the connected clusters. And the key idea for this is that here the operators are still local in the sense that they are direct products, so that you can, for example, verify the disconnect clusters explicitly cancel. And also, we finally need this simple bound t to the p on this small h, and that's where we need this measurement assumption to hold. Okay, so let me conclude. So we proved that Heisenberg limit is robust against generic interaction before some order 1 time, and for GHZ metrology, we devised this LCC measurement protocol to do it. And for outlook, I guess it's interesting to see whether our measurement assumption is necessary for the sampling problem. And it's also interesting to consider our work in the marginal setting of, say, multi-part estimation or Hamiltonian learning problems. And finally, you can view our work as some locality analysis for quantum metrology. And I would just to note that there are also other recent works on this kind of line of research. So, for example, one can bound how fast one can generate quantum fusion information using local dynamics, using Lie-Boston bounds. And in our ongoing work, we also show that for such locally generated metrological resource states, how can you measure in some sufficient local way and in a optimal sense. With that, I'd like to thank you for your attention, and I'm happy to take questions.
Thank you. So questions? Maybe I can ask a quick question. So, I mean, maybe it's related to your outlook. So you considered V as sort of like something bad that's happening to you, but what if you like didn't start with a GHG state, right? So could you also, I guess, have V create the kind of the entanglement that's needed to get Heisenberg limit?
Yeah, I think there are previous literature already on for devising specific kind of V to either generate the original initial metrological resource states or to kind of stabilize the sensing part.
But what if V is sort of generic? So generic V wouldn't work, right? It has to be a specific V, right?
I think so, because GHZ is a very highly structured state. So that's my guess. Yeah.
Questions?
Yeah, thanks for this nice talk. I was wondering, did you also think about generalizing this to a case where you where the V is unknown, but you only have some properties of it, like maybe bounded, and you kind of have to learn it on the way?
Yeah, that's a good question. So I think in some sense you can view it as this kind of how to generalize this to like multi-parameter sensing. Uh, uh, but I think there like it's really hard to still restore this Heisenberg limit scaling because you can view this kind of unknown V as some like decoherence and which reduces to SQL in general. Um, so there, maybe you can ask for uh, like optimal scaling of the evolution time t, and I think that's mostly studied in this kind of Hamiltonian learning literature.
I guess your V could completely mask the omega, right? The V could have another term that looks like your omega Z in there. More questions? I mean, I can ask one more. Like, can you show your first sampling slide where you define this H of S? It's a very silly question. Yeah, what is this e to the minus is? Is this even like Hermitian? Like, what's going on there?
Yeah, I just go through this very quickly. So this h nu, where nu is some finite number, is a time independent geometric local Hamiltonian, and I just assume that the total Hamiltonian is just like it has a finite number of Fourier components where each component is this h nu.
So is H nu Hermitian?
Yeah. Yes.
So then these omega nus come in pairs or
Oh
something?
yes, sure.
I see.
Yeah.
More questions?
So in your problem, you consider the perturbation in your Hermitian problem. In Hermitian term, that is you perturb your Hamiltonian. So V as an unwanted phase. Can I realize it as? Can I realize the V is an unwanted phase, right?
What do you mean by phase?
Since omega Z is omega is the
Oh, I see,
parameter
sure.
that we want to estimate, and then
I see.
V probably is an unknown signal that we
I
want
see.
that we don't want. So if the perturbation is, for example, other channel, for example, random poly channel or other noisy channel. So under that condition, is the Heisenberg limit still robust?
If you consider like this general channel thing, I think it goes back to the decoherence setting where it reduces to SQL in general. And the only way you can like restore HL is where you have very fine-tuned structure on your channel. For example, you have JC metrology, but with poly X error. And then in that case, at least with some error correction, you can restore that Heisenberg limit. But in general, it's not possible.
Okay, thank you.
Mhm.
More questions? We still have time. Well, if not, I guess let's thank the speaker again.